Okay, I'm recording here. So let us look at the presentation. All right. So last time we talked about basically the microstructure, which was the last thing that we said, and we said if we were going to do any investigation in the area of material science, structure of the material, basically you can say microstructure is required to know, and that's why we use optical microscopy or scan or electron microscopy to do that. We said the things which affect the way the microstructure affect the characteristics or the properties of the material, where the number of phases, as we said, present, their properties, their proportions, their properties as well, and the composition, let's say, the manner by which they are arranged. And I've shown you some examples here, which we said we had the like this. This is a microstructure. It's needle-like islands, for example. These are islands, separated islands. It could be continuous islands, which are much bigger islands and coming continuously linked together. I did not have a figure for that. We had fine dispersion, for example. You have a fine dispersion. This is an example. For example, here you have lamellar configuration. Lamellar configuration, where do we have this is a lamellar configuration, for example. These are not quite, I would say, but we will see more of the lamellar configuration in the perlitic structure. I forgot to put the perlite structure here, but anyways, banded structure. This is banded. You see, like you have lines of a phase and the other phase. Coarse and blocky structures there. Again, I don't have that. Networking. This is an example of networking that you have here. The way the microstructure looks like affects the behavior of the material also. So these are ways where the microstructure of the material affects the behavior of the material, starting with the number of phases, what the phases are, what are the composition of the phases, the proportion of the phase or the phases which are present, also the way, and this is what I'm saying here, the manner or the way in which they are distributed or arranged. Continue today. Guys, you're hearing me well?
اي دكتور.
Okay.
Yes, doctor.
So today, let us continue on that track. Let's look at what are now. Today, let us look at to start looking at what equilibrium phase diagrams are, and let us use those and determine what we said we are going to determine. So, what are phase diagrams, or what are basically normally it is named phase diagram, but we officially name it equilibrium phase diagram. And I want to insist today on calling them equilibrium phase diagram because we want to know why we call it equilibrium phase diagram. So phase diagrams are graphical representation, as we have seen in the simplest one. If you remember, simplest one is a graphical representation, as you can see here. The temperature and the composition there. And what does it do? Basically, it does, which shows a graphical representation of what? Of the number and quantities of phases which are there. How many? What, and how many? And this is what? How many phases do we have, and what the phases are basically. So this is, if let's say, it's a representation of the number and quantities of phases that exist in an alloy. So you have an alloy, you can say from its phase diagram how many, the number and or quantities and qualities, like which phases are present in a given alloy at a given composition, temperature, and pressure. We will come to pressure later. In this slide at the end, we will talk about that. Why do we call it equilibrium phase diagram? Well, basically, it's explained here, but let me explain it in another way. Yani it is mentioned in these two paragraphs, but let me explain it also in another way. Let us start with why for the question why we call it equilibrium phase diagram. Yani why calling it equilibrium phase diagram? Let us start with talking about the diffusion. Diffusion is the movement of the atoms, basically. When we have a material which changes its structure, going from one structure to another structure, what happens, or why does it happen, and how does this happen? It happens by the movement of the atoms in it, or the movement of the molecules in the material. So this movement of the atoms in materials are different from gas. For example, if you leave gas in a small in a small area, then if you leave it out freely, it's going to expand and expand from high concentration to low concentration. So the diffusion in the atoms in the gas is very fast. Hello? Somebody said something?
لا دكتور بس طلع صدى مرة من
طيب خلينا نكمل. So the diffusion, which is the movement of the atoms in the gases, as you can see, is very fast. In the liquid, on the other hand, also there is diffusion. For example, you are mixing two things here. It diffuses from high concentration to lower concentration in order to have homogeneous concentration there. And the diffusion, it's slower than the gas, but it is fast also. But the diffusion in the solids, as you can see here, in the solids, also diffusion happens. How is it that material goes from one crystal structure to another crystal structure? Yani when you change the temperature of the material, for example, it changes the structure of the material, which changes the phase of the material. How does that happen? It happens by the movement of the atoms. But the movement of the atoms in the solid is much slower than the liquid and the gases here. So the movement, the diffusion process in the diffusion process in the solid material is very slow. So to start from there, if we know that is the case, now let us go and see why do we call it equilibrium phase diagram. When we heat treat any material, when we heat treat it, يعني نسوي له أي معالجة حرارية, if we heat it up, let's say to 800 degrees centigrade, and then we cool it down. When we are cooling it down, the transformation in the material takes time, as we said, because it is a solid. So it goes from it is a solid. So in order for it to transform from a certain crystal structure or phase to another phase, it requires time because the diffusion process in the solid is slow. So in order for the material to transform, you need to give it enough time more than the diffusion process which is required, which is the movement of the atoms, in order for the transformation to complete. If you leave the material to transform correctly, and you leave enough time for the diffusion process to complete, for the transformation to occur, material normally goes to distances between the atoms or arrangement of the atoms which are at the room temperature at its lowest energy level. So this is what we are saying. So the presence of the difference. So what happens? The material normally goes to lowest energy. And this is an attitude of all materials actually. But if you don't give it enough time, if you cool down, for example, fast, what is going to happen? The material will not be able to transform. The transformation will not be complete. The material is not having enough time. Why? Because you are going faster than the diffusion process. The atoms cannot move faster If you are going down or cooling down faster than the diffusion process, then the diffusion process will not be complete. At the end of the day, what you are going to get is a non-stable configuration, is not a stable phase, is not, the material will not be at its lowest energy level. Phase equilibrium is not achieved. The material that you are going to get, the phase that you are going to get by doing that will be what we refer to as a non-stable phase. So this is what we are saying. Stable or equilibrium configuration of a system is achieved when sufficient amount of time has elapsed or given that transformation completes or occurs. If you don't allow the transformation to complete, because the diffusion process is very slow, so you need to go very, very slow in your cooling process in order to allow for the transformation or the diffusion, which happens by the diffusion, to occur or complete. And if you allow it to complete, phase equilibrium will be maintained in the material. Otherwise, the phases which you will be getting will not be at their lowest energy level, and that's why they will not be stable. Why? Because if you leave them, then obviously, or you develop or you introduce any stimulation, they are going to change. Because why? Because material will always tend to go to its lowest energy level, and these are not stable, and they will go to other stable configurations then. So this is why we call it equilibrium phase diagram. Why do we call it equilibrium? Because the phases that this phase diagram, which is called equilibrium phase diagram, can be used in order to predict the material which gets developed by heat processes or by heat treatment, which are very, very slow only, because they can only show how equilibrium phases develop, but not non-equilibrium phases. And that's why we have a precondition when we want to use the phase diagrams. We have a precondition. The condition for that, for the using of the phase diagram, is that the cooling process is done very, very slowly, slower than the diffusion process in the materials. Is that clear? شباب, is that
يعني
clear?
دكتور هذه الفترة تكون يعني ساعة ساعتين كم يعني؟
ما يعني it's not a matter of ساعة ولا ساعتين. The concept which I want to reflect here أول شيء, I am concerned with the concept إن تفهم يعني شنو equilibrium phase diagram. ليش نسميه equilibrium phase diagram? The speed or the rate that you want to do the heat treatment has to be slow enough, slower than the diffusion process, in order to get equilibrium phase diagrams. And that is why we call it equilibrium diagram. The question is not كم ساعة أنت بتاخذ ولا كم ساعتين. This is another story الحين. But we are talking about the question, why do we call it equilibrium phase diagram? Is this clear?
Yes, doctor.
Any questions? As I'm saying here, need sufficient time, sufficient amount of time. And generally speaking, this sufficient time will be time which allows the diffusion process to complete. If you don't allow it to complete, the transformation will not be complete. The material which will develop will be a material which did not complete the transformation, and that's why we call it a non-equilibrium or a non-stable phase, which will be, again, it's at room temperature even it's going to again want to transform to other phases يعني. Okay, so if this is clear, we want to now start with the phase diagram. We explained what is the phase diagram first of all, and then we explained why do we call it equilibrium phase diagram. Now, in the present discussion, we are going to focus on binary phase diagram. What is the meaning of binary? A binary phase diagram are phase diagrams or systems for the phase diagram with two components, basically. We are going to restrict ourselves to that because we don't want to make it very difficult, and we are not going to cover all the phase diagrams, the important ones, and those important ones for us in mechanical engineering are actually binary phase diagrams. So binary phase diagram for an alloy with two components, as we said. So if you have a system of two components like the copper nickel, it's a system with components are copper and nickel. This is binary, two components only. And also we are going to we are going to stick to binary phase diagram with temperature and compositions as variable only, and the pressure which I mentioned here is kept constant at 1 atmosphere. Of course, the pressure, we cannot ignore the pressure because composition has an effect and should have an effect on the phase diagram. Temperature has a big effect as well, and pressure should have a big effect as well. And in your thermodynamics and your fluid mechanics, whatever, you know the effect of the pressure in boiler, in turbine engine, whatever, the pressure has a big effect on the outcome of any calculation that you have and the effect on the material as well. But for us in material science and for all practical purposes, we always do our, we are not concerned with what happens in a boiler with high temperature, with high pressure there. When we do our heat treatments, we normally do our heat treatments at ambient pressure, which is 1 atmosphere. In all companies, in all factories, they do it in open air. They don't do it even in the furnaces. They don't do it in a closed vessels, for example, to see the pressure, how much it is. Unless you go to other planets, for example, where the pressure is different, then we will be concerned with that. So in our case, the pressure is kept at a constant of 1 atmosphere, which eases the matter of dealing with the phase diagram. And this makes the life much easier, because talking about 2-dimensional aspect rather than 3-dimensional reduces the complexity of the problem drastically. It's not little, it's a lot. It's a lot easier for us to consider the pressure as constant. And as I said, for all practical purposes, pressure is kept actually at 1 atmosphere. We will focus on 2 simple types of phase diagrams, the binary isomorphous and the binary eutectic. So we will be dealing with, and we will see what each one of these mean. So we will start with the binary isomorphous phase diagram. To start with, binary isomorphous phase diagram, the copper nickel system is one example, and it is an important system. Again, what do we mean by binary? Binary, we mean a system of 2 components. So in this case, for example, we have copper and nickel. Here, that's nickel and that's copper. Isomorphous, what does isomorphous mean? Iso means basically 1. Iso means 1. And morphous comes from the word morphology. And morphology basically means crystal structure. So you are saying iso, yani 1, morphous, morphology, yani 1 crystal structure. So basically you're talking about a system of 2 components with 1 crystal structure only. So the crystal structure is the same. This is what it means, binary isomorphous. And we will see this behavior in this system that we are going to talk about, which is the copper nickel system. One of the simplest phase diagrams, or actually to understand and interpret, is the copper nickel system. So how does the phase diagram look like? Again, this is the phase diagram. This is the temperature axis, as you could see here in degree centigrade. We are used to degree centigrade. We are not used to degree Fahrenheit, although the degree Fahrenheit is given there. But I'm sure you don't have a feeling for degree Fahrenheit. You have a feeling for temperature in degree centigrade because we normally use it. So we are going to stick to that. And that is the composition axis, the composition in weight percentage. You have it in atomic percentage there as well, but we are, again, that is more difficult to realize or understand. This is much easier to understand, which is the composition in weight percentage. The composition here, as shown in the phase diagram that you have here, it starts for the nickel. Basically, it starts with 0 nickel, 10 nickel, 20% nickel, 30% nickel, and so on and so forth up to 100% nickel. So if this is the nickel, then since we are talking about binary phase diagram, we have only two components, copper and nickel. If 0 nickel is there, so you have 100% copper. 10% nickel, this means you have 90% nickel. 20% nickel, you have 80% copper, and so on and so forth. All right. Next, let us look at the lines there, which we normally call the solubility lines there. That line, as you could see in the phase diagram here, above that line, everything is actually a liquid. And that's why this line, basically, we refer to it as the liquidus line. So this is the liquidus line. And the other line here, as you could see there, below that line, everything is a solid. And basically, we call that solid alpha solid solution. So the alpha solid solution. So below that line is all solid, and that's why we refer to it as the solidus line. Between these two lines, you have two phases, the alpha solid solution and the liquid solution. Above that line, everything is liquid, and below that line, the solidus line, everything is solid, and that's the alpha solid solution. Now, notice one thing, that how this is, before we go there, let's notice one thing important here. If we look at pure metals, like the pure nickel, for example, pure nickel is where, that's the pure nickel. This is the pure nickel, and that is the pure copper. So if you have 100% copper there, what is the melting point of copper? You can see it from the phase diagram. If you heat up that copper, once you reach to that point, everything is, just before you reach to that point, everything is solid. Once you pass that point, you are in this area, which means you are in this area above 1085 degrees centigrade, which is given here, above 1085 degrees centigrade. Once you reach above that temperature, you are having a liquid. So basically, the melting point of pure metals can be also determined by the phase diagram. What is the melting point temperature of pure nickel, for example? You can see it is much higher, is that point. Once you reach this point, just above that point, which is 1453 degrees centigrade, the solid metal transforms into a liquid metal. So as you could see, pure metals, how do pure metals behave? When they transform, or they melt, actually the melting or solidification occurs across a single point. Unlike the alloy. If you have a mixture of two, or if you have an alloy of whatever composition between the nickel and copper, you see that the melting does not occur directly. This is called direct melting, which happens across a point. Here, when you have alloy with different composition, the melting does not happen directly. Actually, you go across the solidus line, then the liquid starts to develop, and the liquid increases in developing until you reach the liquidus line, then everything goes to the liquid. So this is indirect. We call that indirect melting, but here we call it direct melting. And this direct melting is a behavior for pure metals only. So if you have a metal which is not pure, direct melting is not going to happen. This is an important characteristic of what happens to metals when they are pure and non-pure. I want you to notice this because in the next phase diagram we are going to see something which contradicts that, and we are going to explain that in the next phase diagram. So let's continue with the copper nickel system. The phase diagram, this is the same as just another drawing, is characterized by some things. One of the important things that we can the copper nickel system is characterized by it's the complete solubility, which you could see both in liquid and solid. Yani in the liquid, of course, liquid is not important for us. What we are concerned is with the solid. For whatever composition that you are having between the copper and the nickel, if you have 10% nickel, 20% nickel, 40% nickel, whatever the composition is, you have complete solubility of one into the other one. So the copper has complete solubility in nickel, and the nickel has complete solubility in copper. And this is an example of what unlimited solubility or complete solubility, as we could say that. So you don't form, and this is what I'm saying, you don't form any other phase. It's always the alpha solid solution, which has the same crystal structure type, which is the FCC crystal structure. So it does not change. So this is complete solubility, as you could see, and this is why we refer to it as binary, of course, isomorphous behavior. Isomorphous, it has one single crystal structure type, and it is all through with different compositions there that you're having, and this gives unlimited solubility of one into the other. Now, you know from the in chapter 3 from the crystal structures that we studied, what is the crystal structure of the copper?
FCC.
It is FCC. Also, what is the crystal structure of nickel? It is also FCC, right? Both of them are FCC, and that's why you have that solid solution which they form is also an FCC. Now, let us explain why do we have this unlimited or complete solubility of one into the other one, of nickel into copper, or the copper into the nickel. Why the complete solubility is there? So complete solubility is explained by the fact that we have, if you remember, for the conditions in chapter 4, for the conditions of having a solid solution or otherwise different phases forming, we had conditions there. So we said to have, for example, interstitial solid solution, we have to have the size factor. That is one, the size of the interstitial atoms have to be small enough in order to go in the interstitial spaces. In the substitutional solid solution, we said the sizes of the atoms have to be comparable, close to each other, in order for it to be able to substitute it. Also, the other condition which we said was that their crystal structures, the way they make their crystal structure, has to be the same. So here, both conditions actually we have. If you look at the table in the back cover of your book, which I have given you, you will see the atomic radius of the nickel and the copper are very, very close to each other. In addition, both of them display an FCC crystal structure. In addition, if you look at the electronegativity and the valence electrons in both of these elements, the copper and the nickel, you will see them also very, very close to each other. This is how the complete solubility of one into the other one is explained. Why? Of course, this is a substitutional solid solution. Why? Because the size of the atoms are comparable, yani nearly equal to each other. Nearly, they are not equal to each other, of course. Okay, so it makes a substitutional and not interstitial solid solution, so that it is completely soluble one into the other one, because all those conditions actually prevail, and that's why are there, yani are available. So that's why you have complete solubility there. The solid solution is called alpha solid solution, and it is a substitutional solid solution, and it has an FCC crystal structure. As I've already explained that at the beginning, for any composition other than the pure composition, the melting takes place over a range of temperature. Other than the pure composition, in the pure composition, direct melting occurs. Other than the pure composition, any other composition, the melting occurs across a range of temperature. And that is an important characteristic that we want to see in the next phase diagram, not this one. Now, since we have looked at what phase diagrams are, let us now practice how we can use the phase diagram in order to answer those 4 important questions. If we are given the temperature and the composition, of course the pressure is kept constant, right? If we are given the temperature and the composition for any alloy, then we can determine those 4 things. We can know how many phases we have, what the phases are of that alloy, and what is the composition of each phase, and what are the proportions of each phase. These are the important things that we talked about here. We said the number of phases which we have, what the phases will be, their proportions, and their compositions as well. These are important things which characterize the microstructure of the material, and therefore affect the properties of the material, because properties and microstructure are linked together, as we know from the pillars of material science and engineering. So if we want to design properties, we can design microstructures. If we design microstructures, then we can make certain or specific properties of the material. So we can manipulate the properties by manipulating the microstructure of the material. So how can we do that? By using the phase diagram. It's one tool that we can utilize in order to make different microstructure types. So how do we do that? By looking at this. If we can utilize the phase diagram to predict what the number of phases are, and what the phases are, what their compositions are, and what their proportions are, therefore we can use the phase diagram also to design our microstructure, and therefore design the properties which we want. So let us start doing that practice on the phase diagram. And if we have a specific temperature and composition of the alloy, we want to answer those 4 questions there. How can we determine them? Rule number 1, if we know the temperature and composition, then we can know the number, the type of phases present. For example, let's look at this example. If we are at point A, which is at 1100 degrees centigrade, that's the temperature, and we are at 60% by weight nickel, since we are having binary system here. So if we have 60% by weight nickel, we have 40% by weight copper. How many phases do we have, and what are those phases? Let's look at point A. 1100 degrees centigrade is this, and the composition is 60% by weight nickel. That is 60% by weight nickel. So the point is here. At the point A is here. That's temperature and that's the composition. How many phases do we have? Very simple. From the phase diagram, we know that we have only one phase. What is that phase? It is the alpha solid solution. As simple as that. So by the phase diagram, we can determine in the alloy how many phases we have and what that phase is as well. Another example will be at point B. If we were at a temperature of 1250 degrees centigrade and at 35% by weight nickel, so we will go 1200, 1250, 1300. So this is in the middle between these two is 1250, and we are at 35. That is 20 and that's 40, so in the middle is 30, so that is 35, between 30 and 40. So the point actually falls in this area. And once you indicate the point where you are in the phase diagram, you will say how many phases do you have. You basically have two phases. What are they? They are the liquid solution and the alpha solid solution. So you are in the two-phase region basically. As simple as that. This is very simple to locate and understand what you have. And
دكتور
yes.
في الفيس diagrams we will be dealing only with liquids and solids.
Basically, we have solids. We are more interested in solids, but yes, obviously we are dealing with liquids and solids, yes, or a mixture between the two, as we could see here, right? You have a mixture between liquid and solids, right?
No, I mean like we will not look into the gas phase.
I told you at the beginning, we are concerned with solids, right? We are dealing with material science. We are not concerned with gases, and we are not even concerned with liquids. We are concerned with solids only. But in certain phase diagrams, the liquid will be shown as well there. Okay? Because we are concerned with materials, not with other things there. All right. Now steps to compute the composition. Now the second step, determination of phase compositions here. Of course you have explanation here, but I will jump directly. This is explanation you can read on your own. We will go directly to the application. But instead of just reading in there, we will go directly to application. So rule number 2, if we know the temperature and composition, then we can determine the composition of each phase or of the phases which will be present. The composition of each phase could be also determined using the phase diagram. Let us look at an example. Let's say we have a composition of the alloy. The composition of the alloy, C0, is 35% by weight nickel and 65% by weight copper. And let's suppose we are at temperature TA. Where is TA? TA is high enough to go above those lines there. So TA is in this area. So let's say we are at temperature TA and at 35% by weight nickel. So we are at that point basically. So we are locating our point. How many phases do we have here? We have only a single phase. We are in single phase area. What is that phase? It's a liquid solution. So what's the composition of that phase which we are having, which is liquid, will be the composition of the alloy. So basically you are having, that's the composition. The composition of the liquid in single phase regions will be the composition of the alloy basically. So as simple as that, you can determine that. The same thing also stands when we are at temperature TD. So TD will be whatever temperature which will make the material in the single phase region solid here. So if you are at temperature TD and composition 35% by weight nickel, again, how many phases do you have here? You have one phase. What is that phase? It is the alpha solid solution. What is the composition of this phase? It's 35%. It's the composition of the alloy again. If you have a single phase, then it will take the composition of the alloy here. The third case, if we are at temperature TB, and the TB, the temperature which makes the material in the two-phase region. Some people are, I don't know who is this, who is annoying me. I have to put this on silent. Okay. It is the temperature where and the composition where the material is in the two-phase regions basically, when you have the liquid and the solid together. So what happens here? Now if we are at temperature TB and at 35% by weight nickel, if you locate the position you are at in the phase diagram, this is your location. So how many phases do you have? Two phases. What are those phases? Are the liquid solution and the alpha solid solution. What is the composition of the liquid and what is the composition of the solid, since you have two phases there? In order to determine that, we draw a line there which we refer to as the tie line. It's a horizontal line starting from your composition here. You just draw a horizontal line which we refer to the tie line. It's going to intersect the solidus line at this point, and it intersects the liquidus line at this point. From the intersection with the liquidus line, if we erect a vertical there, we get the composition of the liquid. And from the solidus line, if we erect a vertical from there, we get the composition of the solid solution. So this is how we can get the composition of the liquid and the composition of the solid, basically. By drawing the tie line. Oh my goodness, we have a chart. One minute, guys. I'm just putting the chart here on my laptop. Charges. All right. So this is simply looking at this. We have determined the composition of the single phases and the composition of the two-phase regions as well. So if we are at temperature TA, TB, or TD, we can determine the composition of the phases. This is the second or the third question. We show how we can determine having the temperature and the composition of the alloy. We knew how to determine the number of phases, what the phases are, and the composition of the phases in this simple phase diagram. Of course, it will get a little bit more involved when we go to the other phase diagrams, but it is simple also. It's not a big deal. So the last thing that we want to determine also is the determination of the phase amount or the proportion. And the proportion is an important aspect which characterizes the material. How many of the phases you have. And if you have two-phase material, if you have two phases in the material happening, so you have two phases in the material, as we said. So this is one phase and that is another phase. How much you have this phase and how much you have that phase, it matters, of course, in the properties of the material. So now we want to determine the phase amounts. Again, this is explained to you here. I'm going to jump into the example directly. So let's get the laser point better. So rule number 3, if we know the temperature and composition, then we know the amount of each phase given in weight percentage as well. So let us look at the same example that we did before this. For example, if we have 35% by weight nickel, so we are at that composition, and we are at temperature TA. So again, if we are at TA, so this is our position on the phase diagram. This is where we are. We locate ourselves again. Again, to go through all the aspects now. How many phases do we have? We have one phase. What is that phase? It is a liquid solution. What is the composition of that liquid? What's the composition of that liquid? This is the point we are talking about. What is the composition of that liquid? Yalla shabab.
35% weight by carbon nickel and 65 for the copper.
ايش دخل كربون في الموضوع؟
لا بالغلط دكتور. 35 weight% nickel and 65 weight% copper.
Yeah. When you say in the binary systems 35% by weight nickel, that is also enough. Yeah, because obviously it will be 65% by weight copper. Okay, so the composition of the phase here of the liquid will be the composition of the alloy basically. What's the proportion? What's the weight percentage of this phase? Of course, it is 100% liquid. You don't have anything else there. So the weight fraction of the phase is 100%, and this is what we say. So you have weight percentage of the liquid is 100%, weight percentage of the solid is 0, because you have two phases there only in this phase diagram. The same thing at temperature TD, if you are anywhere here in the single phase region as well here. Again, how many phases you have? If you locate yourself here, then you have only one phase. What is this phase? It's an alpha solid solution. What's the composition of this phase? it is 35% by weight. Nickel, what is the weight percentage? It is 100% by weight, you know, alpha solid solution. So the weight percentage of the liquid is 0. You don't have any liquid there. Weight percentage of the solid, of the alpha, is 100%. Now let's look at the point B, which needs a little bit work there. So if you are at temperature TB and the alloy composition is at 35% by weight nickel, you are falling at that point. As we said previously, in order to determine, actually, before we do that, in order to determine the weight fraction of each phase, you need to determine the composition of each phase as well. So I mean, this gets that. So if we are at this point, in order to get the to answer the questions, I mean, how many phases do we have at my cursor? We have 2 phases. What are those phases? It's liquid plus the alpha solid solution. What is the composition of those phases, which is the liquid and the alpha solid solution? You have to draw a tie line. You intersect with the liquidus line and get the composition of the liquid. You intersect with the solidus line, you get the composition of the solid. So C alpha is 43% and the C liquid is 32% by weight nickel. How do we get the proportion or the weight fraction of each phase? Since you have 2 phases, how much do we have alpha and how much do we have liquid at that temperature? Basically, we use what we refer to as the lever rule, and this is what we do a tie line, and then we will be using, you know, lever rule. Let us use the lever rule, and then after this slide we will see where is the lever rule coming from. If we apply the lever rule, basically, let us call this part of this is the tie line. Let's call from this point to that point S, and from this point to that point R. That is arbitrary, يعني بخيارك تقدر تسمي أي تسمية. If we want to determine now the weight percentage of the liquid, basically if we apply the lever rule, weight fraction of the liquid will equal to it's actually the fraction of the tie line. These are the fractions, the proportions of S to the proportion of the total tie line. To get the proportion of the liquid phase, basically, you look at the part or the segment of the tie line which is far from the liquidus line and divide that by the total tie line length. So you can say the weight percentage of the liquid is equal to S divided by R plus S, and as we are saying here, it's S divided by R plus S. Unlike determining the composition, when we determine the composition, we intersect with the liquidus line and find the liquid composition. Unlike that, in this case, you actually, the liquid, the proportion, you take the far segment actually from the liquidus line. So it is S divided by S plus R. And if you wanted to get the proportion of the solid, you will take R divided by R plus S. It's the opposite. It's the far segment from the solidus line divided by the total tie line segment. So in order to determine S divided by R plus S, S is equal to what? S is basically equal to the length of this segment is equal to 43 minus 35. So to get that segment in terms of composition, it's equal to 43 minus 35 gives you S, and this is what? That's 43 minus 35. And to get the total segment, which is the S plus R, you just basically subtract 43 minus 32 gives you the total segment length there. So you say 43 minus 32, and of course multiply by 100, you will get 73%. So this means the weight percentage of the liquid at temperature TB is equal to 73% by weight. Of course, the 73% by weight only. There is nothing else. We are not looking at composition here. If you want to get the weight percentage of the solid solution alpha, Again, you want the solid solution alpha, you use the lever rule, you will say R divided by R plus S. So, and this is what we are saying, the far segment, as we said from the solid line, the far segment divided by the total tie line length. R is equal to how much? R is equal to basically 35 minus 32. And that is the R value, and the R plus S will be 43 minus 32 in the same way we had it here. So it's 43 minus 32. If you divide those, you will get 27%. The weight percentage of the solid will be 27%. Of course, since we have binary system, and instead of that, we could have said, we could have said, instead of doing this, since if this is 73%, we could just say weight percentage. If we determine that, we say weight percentage, since we are talking percentage, weight percentage of alpha, and instead of using lever rules again, you can just simply say 100 minus weight percentage of the liquid. صح? Because total will be 100. Actually, these two, if you add them together, you should get 100%. صح? 73 plus 27 is equal to 100. That is, we know. So instead of using lever's rule here also, instead of getting the number this way, you could have just used this. Weight percentage of alpha is equal to 100 minus weight percentage of the liquid. So this will be 100 minus 73, which gives you 27% also. Where does the lever rule actually come from? Well, basically, lever rule comes, and how it is, where do we derive that from?
دكتور.
Yes.
Times is up.
The time is up. Just 2 minutes. Just this slide when we are done. It's a simple slide. So it comes from two equations. First of all, we can use the weight fractions. So we can use the equation saying weight percentage of liquid plus weight percentage of solid is equal to 1, or 100 if you want. And from the other equation, which is the conservation of mass, or we can also call it the rule of mixture, the composition of the alloy is equal to the weight percentage of the liquid times the composition of the liquid, plus the weight percentage of the solid times the composition of the solid. From the first equation, for example, you can say this, you can transfer this here, and you can say minus weight of the solid. So you will cancel this from here. So you can say, or the other way around, basically. I could say of the liquid in order to determine the first one and cancel this one. So you can do it both ways. So the weight percentage of alpha is equal to 1 minus weight percentage of the liquid. So you can cancel out that and substitute for the weight percentage of the solid here. So this will become, will become 1 minus weight percentage of the liquid. We just substitute this here instead of this, instead of that. In the equation there, you will only have weight percentage of the liquid. Take everything on one side and the weight percentage of the liquid on one side, you will be getting that, which is basically the lever's rule that we have used. You can do the same thing with the weight percentage of the solid. Instead of moving that there, we will be moving this there, and we substitute there, and we will get the same formula for the lever's rule. Another way of looking at this is a geometric interpretation. Basically, there you can say, like, you have an equilibrium. You have an equilibrium case. The weights are considered like forces there, and this R, of course, R arbitrary. It's used like the arm. So that's the composition of the liquid. That's the composition of the solid, and it has a weight of alpha. So basically, to have an equilibrium, moment of equilibrium, you say WL times R is equal to W alpha times S. And that's the equilibrium that we're having there. From here, you can substitute WL by 1 minus W alpha, and then just solve, and you will get the same lever rule there as well. Okay, I will stop here. Any questions, guys, about what we did today?
Doctor?
Yes.
I have a question, but it is not related to this chapter. It is related to the hardness.
Okay, go ahead. Go ahead.
I think like in the end of the chapter, there was a question saying that what do we use to cut diamond, and we did not answer that since it is the hardest material.
Since this is being recorded, it's good that you are asking this question. Now, you see, what are applications of hardness? Can you tell me?
Hardness.
Yes, hardness as a property is used actually in designing some materials for certain applications. And if you want to design chisels, for example, صح? You know what's a chisel? You don't know what's a chisel? هاي بالعربي يا شباب الchisel.
ندري دكتور.
نستعمله بالعربي هذا نقول chisel, the metal that you use to break, for example, rocks, to break whatever, صح? The jackhammer, you know what's a jackhammer? On the streets. Hello.
نعرفها.
عارفوننا. For to design the jackhammer or the chisel of the jackhammer or a normal chisel, for a hand chisel, for example, you need the property of hardness, صح؟ عادل؟
صح دكتور.
In tool making, you always need the property hardness, basically. Why? Because actually the material you're designing has to be harder than the material you're going to be. So you need to make sure that the hardness of your material, your tool basically material, is harder than the other materials. For example, if you are drilling a well, you know, what do you use to drill a well? A well يعني حفر الآبار مال البترول أو مال الماء حتى. What do you use in order to cut the rocks in the lower layers of the crust, earth crust? We use diamond bits actually in the drill. There are drill bits which are made from diamond because diamond is the strongest natural material to break everything. So basically you go to diamond. صح? You do that. Another example, you use the hardness in designing, for example, the brake pads. If you know the brake pads, what are brake pads? And يكون عندنا where are we here? Let's just make a new slide here and let's go here. Yeah, you know what's a brake pad, صح? Your brakes work like this, like you have a cylinder and you have pads. You have a cylinder here, that's the cylinder here. Of course the pads are smaller, and you have a pads maybe like that, like your bicycle. You never had a bicycle with the brakes? It had pads which push, صح? The pad pushes there and it stops the cylinder. This cylinder is a cylinder like this. This is where the bolts are, and the tire actually is fixed to that. So how does it work here? It is actually pushed by this power system that you have against that, and it makes by friction, it stops the wheel and the tire, therefore صح, it stops the car. So this property is required here as well. Basically you make your cylinder here, your cylinder, you make it much harder than the pad itself. Why? Because, well, the cylinder is very expensive. Because from the wearing and tearing to break every here to there, you are causing wear and tear, right? And therefore what happens here is that some item is going to wear out the other one. If you use both of them metal, then both of them are going to wear out. But basically
in order to reduce the cost, we use the hardness property to design the material here. We use a softer material here and a harder material here because this is more important and more costly. We don't allow this to wear out. We allow the pad to wear out because changing it is simple and inexpensive as well. This pad is maybe 6 dinar, 5 dinar, but the cylinder is maybe 100 dinar. So therefore we use this material hardness much less than that material hardness. When they due to the friction between them, when they wear out each other, this is going to wear out, but not this one. So this is where hardness is used as well. You have different applications of hardness as well. Now, your question, the guy who asked, now how do you cut diamonds? Diamond, he said, is the hardest natural material, right? When it comes to the design of diamonds, you don't have actually freedom to do that. We use, what do we use to cut diamond? We use also diamond, but what? We use a single crystal diamond. The diamond that you use as a tool to cut basically is a single crystal diamond. But the diamond material that you are having here, which you normally cut, is a fully crystalline material, right? So the jewelry maker there is not very free in cutting the diamond. Why? Because he cannot go and cut the diamond from here. This is a single grain, single crystal here, right? If he cuts from there, his tool might break. So what he does is that he goes in the weak parts of the diamond at the grain boundaries, which are bonded less. So this is the weakness of the structure there. So he goes and cuts from there. It's easier to cut from here, and that's why he has a freedom to make certain shapes with the way the diamond crystals look like. Basically, he cannot cut through anywhere. This is how diamond is cut. Clear, guys?
Clear, دكتور.
جوابنا السؤال. Okay. So if you have nothing there, we have to stop because the recording will go very too long. We have to stop the recording.